Okay, in today's video, we're going to be demonstrating some of the improvements and extensions we've made to the compiler since we did the code generation. The first expansion I want to show is global variables. So previously, the only kinds of variables were local variables, which can only be accessed inside of the scope they're declared. But here we have global variables. So we have a global variable x declared on line 2, and we have a separate function that changes the value of x and prints it out. So by calling this function, it'll operate on this x variable even though it's declared in a different scope. And if I create a few more of these, we should see, so every time it's called, it'll increase the number printed out. So we should see the numbers from 1 through 5 printed out. So if I compile it and run the assembly, and global variables work by storing an extra stack pointer or stack frame on top of the other stack frames, which stores all the global variables, and that special stack frame has S10 pointing to it. So if I run this assembly, you see 1 through 5 printed out. Very good. The second feature we added is division and modulus operators. Our division operator just divides numbers. It's a pretty useful operation to have. So, for example, we can compute 63 divided by 7, which is 9. We only have integers in our language, so if it doesn't divide evenly, it'll always round down. So 34 divided by 5 will round down to 6. And to get the remainder, you can use the modulus operator, which is the percent sign. So since 34 divided by 5 is 6, with 4 left over, this line will print 6, and this line will print 4. So we should see a 9, 6, 4. And they're simply implemented using the RISC. 5 has a remainder operator and a division operator as part of the extension. So we're just using those to implement this. And if we run it, we'll see the correct numbers get printed out. Our third minor addition is for loops. A for loop simply is a different way to create a loop where there's an initializing condition, which is usually a statement that declares a variable, a condition which checks if the loop should end, and then a statement that runs after each loop iteration that updates the initialized variable. So this simple code will start with 1, multiply it by 2 every time until it gets over 100, and print out each one. So we should see numbers where each number is double the previous. And these are implemented in the assembly the same way while loops are. So actually during parsing, we produce the same output as a while loop would, which just involves checking conditions and jumping to a certain label if the condition's met. So if we run this, we'll see the correct numbers get printed out, and it stops before it reaches 100, because the next number would be 128, which is more than 100. So here we demonstrate all three of these features combined in a program that computes prime numbers. So it uses a for loop to loop through all the numbers 2 to 100, and uses a global variable so that this other function can use it. And this function just goes through all the possible divisors and uses a modulo operation to check if it's divisible. So this can check if a number is prime. Let's compile this. And we'll see all the prime numbers from 2 to 100. It's a little slow. This isn't the most efficient possible program, but it will work and print all the prime numbers up to 100. So the major feature we added is objects. So this is the syntax for creating an object. Objects can have fields and methods. You can create a field simply using the variable declaration syntax like this. So this object has a field called x, and you can create a method using the function declaration syntax. So methods can return local variables, like this one, which simply constructs a local variable and returns it. They can return fields, so this returns the field of x, and they can also modify the object's fields. So the set function does this. It sets x to a new value. So here's a main. So you don't need to call a constructor. Objects are, because every field has to be initialized. So you don't need constructors because every field is already initialized. So my object.x, you access fields with the dot syntax. This will just print out 11. You can set it to 5 like this and print it out. So this will print 5. Return local will print 8 because it's the local variable defined in the function. Returning the field just returns x, which is 5. And if you set it to 17 and then print it out, it'll print the new value. So let's see it compiled. And objects are implemented kind of similar to global variables. So objects are also stored in that top stack frame that S10 is pointing to, because you might need to access an object for multiple different functions. So if we run this, we'll see these are all the numbers that we said would print out, and they're printed out. And finally, I have one last example that uses objects in conjunction with some other features. So this is a program that generates Fibonacci numbers, but all the logic for generating the numbers is in this object. So it kind of acts as a generator, storing the next and previous values, and then it just adds them together to get the new next value. So this main function, the loop in main, will just print out the first 20 Fibonacci numbers by just calling getNext over and over again. So let's demonstrate this. And yeah, here we see the first 20 Fibonacci numbers. So this has been a brief overview of the new features we've added to our compiler.